Um, now I'm going to record. Small liberal arts college up in New York. It's known for being really snowy up here and really cold. I'll talk about that a little bit. But I'm a computational chemist, and that usually scares a lot of people because they have, post-traumatic stress disorder for being stuck in quantum or not really knowing what's going on in thermodynamics. But I promise you, I'm going to try to limit the numbers. No one will have to do any tough integrals or anything like that. It should be an easy to comprehend talk. So I'm going to talk about two applications. One has to deal with something called the molecular corking effect and hydrogen storage. The other topic I'm going to discuss is about a ubiquitous, infamous pollutant called perfluoroalkyl substances, or PFAS, and a little bit about them. So during the talk, if you have any questions, feel free to raise your hand or shout out as we go along. I will have questions at the end too. I'm comfortable addressing them in either way. Okay. So let's get moving. So a little bit about me. Before we go through the talk, I feel like it's always a good idea to make somewhat of a personal connection if possible. So I describe myself as a simple country chemist. When people go, oh, you're from New York, they imagine New York City with a lot of hustle and bustle. I live in a town with about 8,000 people in it, which is way less populated than New York City. I'm also about 8 hours away from New York City. I like to hunt. I like to fish. Do you guys know what curling is by any chance? Has anyone ever seen curling? Can they raise their hands?
Curling. Curling. No? Yes, somebody does.
Yeah.
See.
So I don't know if you can see my cursor over here, but we do a little bit of backyard curling where it's cold enough where we have ice and we'll curl ourselves out there. Usually it's a big drinking affair and whatnot. And then here I'm ice fishing. So it's easy about this time of year to go out on any pond or lake, drill a hole in the ice and fish on top of it, which is interesting. The other thing is I really like to explore different spots. So this is actually an abandoned graphite mine out by Albany. I went exploring down in there, and I live out in the middle of nowhere with my wife and my kids. So just to give you a perspective. Now, a little bit about how cold it is. So I've marked Helsinki, Finland up here. I'm going to be going for a training. Here's where I'm at in Allegheny. Here's where you guys are. So my wife is coming with me on this trip, and she said, oh, we have to pack. It's going to be really cold or whatnot up there. And I actually checked the temperature of Helsinki, Finland versus Allegheny in the United States. And it turns out it's actually colder in Allegheny right now than it is up in Helsinki near the Arctic Circle. So to give you a plot, up top is the average temperature in per month in Allegheny, New York, and below is the average temperature per month in Helsinki. So you can see our average temperatures, we actually get about the same level of cold as Helsinki, but we get a little bit warmer in the summertime. Now let's put that in comparison to where you guys are. So in this plot, what I have is where you guys are. Here's Helsinki in green, Allegheny is in blue. So to give you a perspective on the differences in temperature, that's about what it is. We don't get very hot. I would melt where you guys are. Where we are, it tends to be pretty cold. And usually about this time of year, we have about 2 feet of snow outside. So to give you a perspective, that's where I'm from. I'm from the land of ice and no sun. All right. So let's give an overview of the talk. The first thing I'm going to discuss is why should you trust me? Because you should always think about that when someone's speaking to you, if they're worthwhile to listen to or not. Then we're going to go into the two different topics about hydrogen storage, where we're going to talk about a little bit of organometallic surface chemistry there. And then we'll go into PFAS or perfluoroalkyl substances. Okay. Are there any questions so far? No. Okay. So why should you trust me? Well, I've won a couple of NSF awards or grants, so a lot of the the two grants that I've won a regular NSF grant for my work on perfluoroalkyl substances. And I've also won an NSF Career Award associated with my work towards hydrogen storage. I have published 32 peer-reviewed publications on a variety of different topics involving computational chemistry. I've gotten multiple grants, not only from the National Science Foundation, but the American Chemical Society Petroleum Research Fund and the Henry Dreyfus Research Foundation, which helps fund my work. The other cool thing is I'm a primarily undergraduate institution. So like you guys, there's no graduate students. It's all undergrads who do the work with me. And then I'm also an external reviewer for a couple things for the Department of Energy and Department of Defense. Okay. So let's get right into it. Let's talk about the first topic, hydrogen storage. Hydrogen is an alternative energy that we're seeking to replace fossil fuels because one, hydrogen is clean. Does anybody know what you get when you burn or oxidize hydrogen gas? So what chemical do you produce when you burn or oxidize hydrogen? Any ideas?
Water.
Yeah, water, exactly. We got a lot of water on the planet. It's not as bad as carbon dioxide. The other thing is to get fossil fuels, we typically have to mine in the ground. Another interesting fact about Allegheny, New York is we have a lot of oil drilling here. So behind my house, it's the closest residential spot in Cattaraugus County next to an oil well. So I'm trying to find ways to phase that out. So our other countries, so Japan and Tokyo are focusing very heavily on hydrogen storage. The United States is also focusing heavy on developing hydrogen. So what you're seeing here is an apartment complex in Tokyo, Japan. And what this little guy is a fuel cell. And what this fuel cell does is it converts hydrogen into electrical power through different chemical reactions on the inside of this thing. And it actually can generate enough power for all the people who live inside this apartment complex. So they get all their electricity from this fuel cell. Other spots that people are exploring are for transportation purposes. So if people like BMWs, the BMW is focusing very heavily on that area for cars, same with Toyota, but also for flying, for cargo ships and other transportation purposes. So Germany is focusing pretty heavily on this and has a couple different devices to do that. In fact, Germany, I believe last year was the first country to provide a completely hydrogen train for transportation purposes. Okay, so another reason why hydrogen's being looked at is it has high energetic density. So on this plot, what you're going to see is you have volumetric density and you have gravimetric density on the x-axis. Gravimetric density is a way you can think about it is how much energy per unit of mass. Volumetric density is how much energy per unit volume. So what you can see is hydrogen is really high on the gravimetric density. The downside, which we'll talk about in a little bit, it's low on the volumetric density. And really what we need to do is we need to beat these guys. Those are the fossil fuel sources that we're trying to beat for transportation purposes. But if we're talking about heating, we need to beat these ones. Okay. Another important process associated with hydrogen has to deal with the Haber-Bosch process. If you guys can raise your hands, how many people know what the Haber-Bosch process is? Any ideas? No? Okay, that's fine. Where you take nitrogen and hydrogen and you react it and you get ammonia out. This is really important when it comes to the production of fertilizers. So what this is it's a plot of the world's population. What you can see is on this axis, we have the years. On the y-axis, we have the population. And right about at this point where the Haber-Bosch process was implemented. And you can see that the world's population has taken off a lot since then. So we need to have good ways to store hydrogen for the purpose of fertilizers too. So the point of all of this stuff is hydrogen's important. It's becoming increasingly important for transportation purposes, and it's important for life. Now, the big problem is storing the stuff. Trying to store hydrogen is a very difficult process. The other aspect to it is there are safety issues, issues with the storage density, and something called boil off. Does anybody work with liquid nitrogen in the room or other cryogens? Yeah, a little bit. So you'll probably get a little bit out of that portion, but I'll talk about what blow off is and how that uses up things. Okay, so the major problem. Hydrogen is renewable, but storage under really high pressures or just storage in general is unsafe. Does anybody know what these two pictures are? Or like what event they're from? Yeah, go for it. If you know it, yell it out.
Challenger.
Yep, this one's a Challenger explosion. Really bad thing happened there. They had liquid hydrogen and liquid oxygen. An O-ring gave out and it caused an explosion. What about this one on the right? Anybody? That one's the Hindenburg explosion. So that happened around World War II. This Zeppelin was filled with hydrogen, caught flame, and exploded. Another issue, this actually happened near the beginning of the pandemic. This is a hospital. Hospitals have compressed oxygen in them, and there was an oxygen explosion that completely leveled this hospital. So it's not just hydrogen that suffers from these safety issues. It's all sorts of gas storage. Okay. Another issue is if you, again, on this plot, this is kind of a cartoonized version. You have the tank weight associated with holding whatever we're looking at, and you have the tank volume. So what we really want is we want to be in this region of gasoline, where we have light tank weights and we have small tank volumes. Hydrogen's really not at the point of being within this gasoline region. But we really have only hit the lower limit of storing the hydrogen. The other issue, this is a liquid nitrogen dewar. If you've been near one before, you know that it hisses all the time. It's constantly degassing. The reason it's doing that is pressure's building up on the inside of this thing. So you have liquid nitrogen being converted to gaseous nitrogen. And as the pressure builds up, it's got to relieve it, or you basically made a bomb. Every time that thing hisses, you're losing more and more nitrogen. So actually, if you leave a tank of liquid nitrogen, and I'm guessing in your guys' warm environment, it probably depletes itself over the tank or over a week or so. So you lose a lot of gas from that. Okay, so what's being done in terms of hydrogen storage? I'm going to talk a little bit about this first one, but just know other people are exploring different avenues for storing hydrogen. A lot of people are trying to use metal organic frameworks. They're basically crystals that suck in hydrogen and store it that way. There are metal hydrides, where you mix metals and hydrogen and you squeeze that under really high pressures, and it forces the hydrogen to stay as a solid. And then there's something called clathrates, which are really cool. I highly suggest you YouTube them if you ever get the chance. Basically, you have water storing different gases, and you can see that somewhere else. But that's the main spots that people are looking. The one that I'm really focused on is adsorption and something called the molecular corking effect. Are there any questions so far? No? Okay. So when it comes to the molecular corking effect, what we have is we have a surface. It typically is made out of an inexpensive or a cheap metal. Then we have a catalytically active metal, just a couple of them on the surface. What happens is the hydrogen meets this catalytically active metal. It splits apart from molecular hydrogen into atomistic hydrogen. And those H's can scoot around on the surface. Now, the problem becomes this hydrogen could just meet back up at this catalytically active metal and escape. It could leave. So, how do we trap it? Well, that's where we utilize something called a ligand, or in this case, my fancy term, a molecular cork. In our case, it'll be carbon monoxide, and it sits on top of that catalytically active metal. So what you can think about it is the hydrogen's now trapped on the surface. The hydrogen's atomistic, and it's way safer. So a couple of people at Tufts University explored this along with some other collaborators. And what they did was they looked at different combinations of single atom alloys. One's made of palladium and copper, and one's made of platinum and copper. And what they did was they looked at what temperature do they need to drive the hydrogen off with a cork and without a cork. So without a cork, they get low temperatures. In this case, for platinum and copper, or excuse me, palladium and copper, it's around 210. For platinum and copper, it's about 230. Now they throw that carbon monoxide on, and what they find is they can drive the temperature at which you need to push the hydrogen up way higher. So they moved it from 210 to 270 in the case of palladium, and in the case of platinum, they moved from 230 to 285. And what they say is the hydrogen's immediately released. It's like popping a balloon. The hydrogen comes off. However, if we want to utilize this at room temperatures, this is still too cold to get there. So what we want to try to do is find a new way. Can we drive the temperature up for real applications to be utilized in transportation or other areas? So what I propose is we look at different ligands or different corks to put on here. Carbon monoxide, how many people are taking inorganic chemistry or an organometallic class right now? Anybody? Raise your hands if you're in an organic right now. No, no one? Okay. It's carbon monoxide binding has a very interesting way it bonds. It donates electron density to the metal, and then the metal actually donates electron density back to the carbon monoxide through something called back bonding. Carbon monoxide is not the only molecule that can do this. One that I got really interested in are known as N-heterocyclic carbenes, or NHCs. They have a wide variety of synthetic techniques, and I actually got involved with a collaborator who wanted to look at complexes of these things, and I said, hey, those are pretty cool ligands. Now, the neat thing about them is they're tunable. You can control how much density that they give off, and you control how much density they accept back in. So they have this cool push-pull mechanism to them. They're really synthetically available, and they're pretty well studied. Now, I'm a computational chemist, but I have a lot of experience modeling molecules on top of a surface. And molecules on a surface behave very differently than they do in the gas phase or in the liquid or in the solid. So what I'm showing here is I'm showing benzene moving closer and closer to a copper surface. And what's being plotted is an electron density deformation plot, where red is the accumulation of charge and blue is the loss of charge. What you can see is as that molecule gets closer, there's more charge that builds up around it on the surface. Now, this has consequences for how the molecules interact on the surface. I know that from a couple different studies. This was also of that same group from Tufts University, where we looked at fluorofluorostyrene on two different surfaces. We looked at it on copper and on gold. And what you can see is on copper, these guys like to form groups of 3. On gold, they like to mainly form groups of 4. And it has to deal with that charge transfer interaction. So changing the surface can drastically change how those molecules interact with one another. Does that make sense to you guys? So these little blobs, these are STM images. They're actually the molecules on top of the surface. So even though they look like blobs, you use a fancy piece of instrumentation to look at those. Okay. In terms of the computational methodology, how many people have any idea what this slide means? Okay, that's fine. This is the computational methodology that I utilize. There are two types of calculations we look at, periodic ones. So those are for surfaces or for solids. And then we have molecular calculations. This is similar to what you might use for Gaussian or games, or if you've ever taken any type of computational software courses in your undergraduate career, you've probably used those types of calculations. So these ones are focused more on solids. Molecular calculations are focused more on molecules. Okay, so again, we know that NHCs are good at donating electron density and they're good at accepting pi electron density. But how do we determine the strength of these things? Well, there are organometallic chemists out there who have come up with really creative ways to do that. So one of the ways is to look at the sigma donor strength through something called the Hun electronic parameter, or the HEP. This is a graphic that I completely stole from a review. Dr. Hun probably won't care too much, but what you can do is you can make a complex where you have a ligand. So you have your ligand of interest, and then you have a probe ligand. And what you do is you do NMR on it, and you're trying to look at this carbon signal. And depending on how the carbon signal shifts, you can actually figure out if the ligands are really good sigma donor or it's a really weak sigma donor. Through that, I could do calculations on anything. So I did some calculations. I'm sorry, there's a giant table with numbers here. I'm being a stereotypical P chemist right now. The molecules we were looking at are this guy, where we're changing these different functional groups. You can see the R1 groups for these points are right along here. All the R2s are indicated along here. And I calculated that HEP parameter. And what we see from these calculations is the weakest sigma donors are ones that have electron withdrawing groups on them. So things like fluorine or nitro groups, they're going to sap more electron density away. And what we see is they have a lower HEP signal. And what that means is they're not very good sigma donors. Okay, so what about the pi acidity? There are two ways that people look at pi acidity. They make either these phosphorus-containing compounds or they make these selenourea compounds. So basically, with the NHC bound to a selenium or to a phosphorus-containing motif. And what you can do is you can do NMR on that. You can see is it more shielded or less shielded from these experiments, and you can get an idea of how pi acidic a system is. So we can do calculations of that. And what we show is pi acidity changes a lot when you change these functional groups. And typically, as you add more electron withdrawing groups, no real big surprise there, you're diminishing or you're changing that pi acidity greatly. Okay, so those are the molecular calculations. Now what I wanted to do was some periodic calculations. Here's what our periodic calculations look like. We have a 3D structure where we have our surface, we have our adsorbate, and this is actually repeated in a 2D plane. Again, I have a giant table of numbers here, but what I really want you to focus on is this binding energy. What the binding energy is, you can think about it as the strength of the interaction between the surface and the adsorbate. The bigger that number it is, the harder it is to pull off that ligand or that adsorbate. So what we can show is, if you're looking at electron withdrawing groups, you weaken that interaction through the sigma and pi type interactions we were just discussing. And the other interesting thing is no matter where you put this NHC on the surface, it always wants to bond to that catalytically active metal. It does not want to go anywhere else. So if there's different bond strengths, that means there are different temperatures at which we can control this thing and store hydrogen to. Okay. Something else that's pretty common in surface chemistry, not only can you control the adsorbate and the surface, but you can also control how many molecules are on the surface. So if you dump a ton of molecules on the surface, you're actually going to change a lot of the interactions that happen, and you change the electronic structure a bit. So to give you an idea what this is a molecule that I'm just going to call a zwitterion. It's adsorbed on the surface, and we have a couple different coverages. This is at lower coverages with less molecules on the surface. This is at higher coverages. And what you can see is as you start to increase the coverage, you get less of these charge transfer interactions happening. So it changes the electronic structure a lot. So if that's the case, how does that impact our NHCs? What we can show is it does change that binding energy a little bit, but not enough to make a huge difference. So even if we want to use these molecules as a storage device, coverage probably won't impact things a ton when it comes to that surface adsorbate interaction. Okay, so what things do we learn from here? The more pi acidic the system is, the weaker that surface binding. The lower that that HEP value means less sigma donation that also weakens that surface interaction. But the real big point to this thing is actually this slide. If we're trying to look for higher temperature quarks when we go to functionalize these things, probably electron donating groups are the way to go. So no matter which way we look at it, if you look at the ranking, as we toss in more more electron adding groups or donating groups, we're going to be able to push these temperatures higher. We're in the process of doing some kinetic Monte Carlo simulations where we can actually figure out what those temperatures are, though. So with that, I'd like to thank all the people involved and the funding agencies associated with my hydrogen storage research. So that's been the ACSPRF, the NSF, and the Camille and Henry Dreyfus Foundation for their support there, and all the people who work with me. Okay. Any questions about hydrogen stuff?
We have at least one, and there's one in the chat. So
Okay, great. Let me check the chat.
anyone in the chat, either go on, okay?
I actually can't see anything in the chat.
Huh? Oh, okay. So somebody asked if you can explain what pi acidity is.
Yes, so pi acidity, let's go back to this plot. Sorry. So pi acidity is, so you have a carbon here on this carbene that has a vacant p orbital. It's how much electron density can that vacant p orbital accept? So how much does it want to pull electron density away from something else? To give you an example of that, let's look actually over here on this side of those selenoureas. So if something is really pi acidic versus something that's less pi acidic, if you have the selenium atom on here, what will happen is if you have something that's not pi acidic, it doesn't really want the density of the selenium, and it'll leave that selenium density alone. But if you have something that really is pi acidic, what it will do is pull electron density away from that selenium, making a stronger bond. Does that make sense?
Thank you.
Yeah, no problem.
I know two more questions. Last time,
We've heard about molecular quarks and how you have been primarily using carbon monoxide, I think was the word. Is it possible to either add another molecule as a binding effect and try to, adjust the quantity so you can either balance, what's the word, I think? Yeah, balance the container and maximize, storage capacity itself.
Yes. So that's kind of the goal. One of the things that we're trying to do. Oops, let me see. I got to the end. There we go. So here we have also looked at changing the molecules themselves and their interactions that way, along with the surface coverage. So what we do show is depending on what molecule you pick here, you can actually impact the catalytic site, and that changes not only hydrogen storage, but it also changes catalytic ability of the surface too. So I don't know if I answered your question completely, but we're also, we're also looking at changing other aspects of the molecule, and we find that that changes a lot. And what we really want to do, we want to up that storage capacity, right? Like you suggested. So metal surfaces weigh a ton. They're not going to be really good at lowering that weight. But what you could do is have a low weight support where the hydrogen will scoot onto this low weight support. They've actually shown that carbon nanotubes can do this, and carbon nanotubes are awesome because they're low weight. They're really strong too. So the goal would be is to take what we're learning from these single atom alloys and plunk it on something that weighs much less. Does that answer your question?
Yes, thank you.
Yeah, no problem.
We have a couple more. Can you see me? Sí. Hi, I'm the only inorganic chemist here. I have to ask a question. Nice talk, and thanks. I was wondering, the NMR experiment that you were mentioning, can you go over and I'm thinking, well, those are cool ligands. Of course, I live up of that. And can that relate somehow to the spectrochemical series, like these experiments and the ability to the backdoning effects?
Yeah. So can you rephrase your question one more time? I'm sorry.
I just wanted to go back to the NMR experiment, and if you could give a little bit more detail of what you're doing with those ships that you mentioned.
Oh, yes. Okay.
Basically, thanks.
So, yep. So basically what we're trying to do is understand, do these NMR, so these NMR shifts give us a clue on how do the molecules interact with the surface? And so we're trying to find relationships between these properties because they're experimental properties that people can measure very relatively easily, and between the surface, because if you understand the bonding that's happening there, you're going to be able to understand how to best build a device and make that device work better. Does that answer your question, or is that a little too weak? Did you want something more chemical?
Yeah, I think that's about it. I don't know if the students would like a little bit more detail on that NMR experiment.
Yeah, so the way that this experiment is conducted is you make an NHC ligand, and then you have, so this is the thing you would make or synthesize in the lab. And then you have this just probe ligand. So that's something that's easily made. You could probably buy it off the shelf. And what you do is you make this complex. And it's like a game of tug of war. You're trying to see which ligand is winning out. So they pull at each other. They're both pulling on the electron density around that palladium atom. And based upon that NMR signal, you can figure out who's stronger in the game of tug of war. So I think it's really cool because it shows you which way it moves. Yeah, go for it. I'm sorry.
Hi, I'm working in electrochemistry and in fact with platinum 111. And I would like to know that if as you increase the absorbates on the surface of the metal, have you considered the effect of the concentration in your model if you consider the lateral interactions between the molecules?
Yes, so they definitely see each other through the simulations. We utilize something called non-local density functional theory, and we also use periodic calculations. So even though I'm showing something that looks like this is our simulation cell, what the calculation really sees more is something like this. So those lateral interactions are across the surface in the XY region, and the molecules in the simulation see each other. So actually they impact each other a lot. That's why it changes the electronic effects. And when I went to that cool animation slide where everyone kind of spaced out, that like charge buildup around here, that is also seen as lateral interactions. And you can observe that through different STM images. But yes, our calculations are accounting for that. Does that make sense?
We have one more.
Have you seen difference in different surface? I think you study the 111, but what about 100?
Yes. Yep, the 111. So in that case, it's made of a single palladium atom, and then you can take different cuts of the copper lattice. So when you think of copper, I believe it's a face-centered cubic structure. It has an ABA stacking pattern, but if you cut it a bit differently, you slice that lattice, you can get this surface. When people do catalytic studies, or at least STM studies, what they want is a nice flat surface. The flattest surface to generate are usually of the 111 cuts, so they go with that a lot of times. I don't know if I answered your question.
Yeah, I was wondering if you have studied different surfaces and seen.
Yep, so we're starting to replace, we've looked at both of these guys, palladium and platinum, with copper, silver, and gold. And we're also exploring swapping out this atom here. It just makes things a little more difficult computationally because you have a lot of unpaired electron density, and you have to work around that or make sure you're modeling things properly. And a lot of issues with surface calculations is there's not really enough experiment to go on in some cases to say if you're doing a good job modeling or you're doing a bad job modeling. So we are exploring that though. Okay. Any other questions on this topic? Do I still have time to go on to my next one or no?
Yes, you do, of course.
Okay.
Absolutely. Let's see the PFAS.
All right, yeah, let's get to the more environmental stuff. So PFAS. PFAS are the big, ugly, mean molecules that you'll see in the media. How many people have ever heard of them? By show of hands, anybody hear about them at all or no?
Yes.
Okay. For those that haven't, I'm sorry if I ruin your day. It's somewhat of a depressing talk about what PFAS are. They're perfluoroalkyl substances. Basically, you can think about them as a molecule that has some sort of head group on them. Typically, it's a polar head group. And then it's a chain of carbons and fluorines. These compounds have really awesome properties. They tend to be utilized in non-stick, non-stain, shirts where you don't have to iron them, even dental floss. They have awesome properties. We utilize them pretty heavily in the United States for many different applications, especially when it comes to food packaging and whatnot. But they originally were utilized for our tanks. We have the best tanks in the world around World War I, World War II, and it's primarily due to these molecules. Okay, so now I'm going to show you some disturbing images. Everybody ready? Okay, so this is up in Michigan. And in Michigan, they have a ton of PFAS contamination from different chemical companies that are out there. And they even have a release saying, do not eat the fish in the area. They also, so being a hunter and a fisherman, that hurts me because I would say about, a quarter of my diet comes from the outside where I get a lot of these things and hunt. So Michigan's an awesome spot to fish too if you ever get the chance. But if you also look, other companies such as Home Depot are starting to say, hey, I need to get rid of utilizing these PFAS. And actually, the EPA is looking heavily at companies generating these things and seeing a lot of problems. And same with Michigan again. They actually had an advisory to not eat the deer if you're hunting because they're so contaminated with PFAS. How many people are religious flossers? I love flossing. I don't know. All my nightmares seem to be connected to losing my teeth for some reason. So I always floss.
Yep.
Yep. Don't floss with Oral-B Glide. It is contaminated with these things quite heavily, which is unfortunate because that's my favorite brand of. Yep. Do not use that
I wish
brand
you
of
could see
floss.
the faces.
Yeah.
Lo que es eso, ¿no? Lo que se usa en teflón.
Sí.
Yeah.
Lo que se usa en teflón.
It's pretty bad. Now the other thing is the United States military had, for anybody who is training for the Iraq war, utilized these firefighting foams, and these firefighting foams have a ton of PFAS in them. And actually, if you look at the contamination around military sites, these limits are actually older. There was one US site that was considered within the safe limits, and all the other ones were significant contamination or extreme contamination. Okay, so these molecules are out there. How do we know what sort of health effects that they have? Well, there have been some studies that show that there are a wide variety of health effects, and especially in infants, a lot of issues there, where you can have thyroid disease, liver cancers, and so on. The other issue is people who are exposed to these, they actually experience a lot of birth defects. So this is Bucky, who is on the right. His mother was working at DuPont in the Teflon line, and she gave birth to a child who had extreme disformities from the PFAS contamination. So there's lots of issues with PFAS and the health concerns. We'll talk more about what's the issue with that and how do we find information about it. But there's a lot out there that you should be reading and looking at and seeing. The other issue is they are on everything. So depending on what food packaging you have, like how many people like microwave popcorn? Does anybody? Stop
We have
eating.
to stop it. Yeah.
Yeah, stop eating microwave popcorn right now. Microwave popcorn has on the inside of it, it's coated with these compounds, and so the oil doesn't stick. So stop using that right now. I'm sorry, I love it. I'll tell you a funny story associated with my wife in a minute. She loved microwave popcorn, and while she was pregnant, I said, no, you can't have any microwave popcorn. She got really mad at me. She's like, you don't know anything. Yeah. So then I knew there was this movie coming out called Dark Waters, and it stars Mark Ruffalo. And it's a story about a lawyer named Robert Billet, and he took on this legal battle against DuPont. It was an extreme uphill battle for 20-ish years. Has anybody ever seen this movie, Dark Waters? If not, if you have Netflix or whatever, try to watch it. It's a good movie. But I contacted him and said, hey, would you be willing to give a talk or talk to us at St. Bonaventure University? And he said, yes. And I got super excited. And I told my wife, I'm like, Robert Billet's gonna talk to us at St. Bonaventure. And she went, oh, well, who's that? I'm like, he's the lawyer I did, like what I told you guys. And she goes, oh, okay, that's pretty cool. Like, well, and Mark Ruffalo stars him in a movie. And she's like, Mark Ruffalo, holy cow. She got super excited about the actor. After he came and talked, he said, don't eat popcorn. And she's like, I get why you didn't want me to eat popcorn now. So she'll trust an actor and a lawyer, but not a scientist who studies this stuff. So we did a showing of it. We had Robert Bob, excuse me, come talk to us a little bit about that. Okay, so watch that movie. He has a book out there called Exposure too. That's a pretty entertaining read. I highly suggest to watch the movie or read the book. Okay. So what things do we know about PFAS? We know because of these really strong carbon-fluorine bonds, they don't break down and they just build up in living creatures. We know that some PFAS cause health problems because actually part of that story, there was a town that was heavily contaminated. All the people there had really high levels of liver cancer, their teeth were discolored, and there were high birth defect rates. So we know that they cause health problems, and we have a good idea of where they are used. Unfortunately, where they are used is like everything. Okay, what don't we know? We don't know which PFAS are dangerous. We don't know which ones are out there because when they make these things, they just make a mixture of them. They don't make compound number 1 and compound number 2 and mix them together. It's just a giant mess when it comes to making these things. And we also don't know how to get rid of them. So we know they're there. We know that they're dangerous. We don't know how dangerous. And the other issue is we can barely see them. So what are we doing about this? We were funded by the NSF. We're hopefully going to be funded again soon, where the researchers who work in my group and myself, we do some quantum chemical simulations. And then the people at the University of Buffalo, they do the identification experiments. Okay, so what's the big problem? Why can't we just do mass spec like Dr. Aga at UB? She has fancy mass specs. Why can't she just run those, find those compounds? She's an environmental chemist. She's been doing this for years. She's really good at it. Why can't they just tell us what's there? Okay, so what I have up here are 2 mass specs for 2 compounds that have the same molecular formula, but different organizations. So they're isomers of one another. And if you look at this mass spec, there is a very little information that you can gather from this. So these guys look like there's a couple different instances where they have different fragmentations, but they really look the same. There's not enough info to figure out what do these things actually look like. So a big challenge is PFAS are really hard to characterize. Those carbon-fluorine bonds are really strong. When you take a mass spec, what you're doing is a lot of the times is shooting electrons to break apart molecules, like in this picture. But when you have molecules that don't want to break apart, it makes it really hard to get a fingerprint. So what can we do? We can do quantum chemical calculations and build these models called quantitative structure retention relationships. So QSRR, and what these do is they provide a mathematical relationship between molecular descriptors or properties of the molecules and the retention time. So what we can do is as they come out of any chromatography, we can calculate what the retention time should be and give justification on what that molecule probably is. So the way that this works is you have a data set. So you have a certain set of molecules where you know the retention time. You split those up into a training set and a test set. You construct models from your training set where you calculate molecular descriptors, you build that model, and then you test your model. And you say it with known things, and you say, is it good or is it not good? Okay. Now, what do we actually do? We calculate molecular descriptors from quantum chemical calculations. So we have to go through this workflow where what we do is we draw molecules, we generate conformers because these molecules are really flexible. And to get good properties, you need a lot of different conformers of these compounds. And then we do quantum chemical calculations to try and predict different physiochemical properties. So things like octanol water partition coefficients or pKa's or like Gibbs energies of solvations. We can calculate all of that stuff. Now you might be asking, why do we need a lot of conformers? So fluorines complicate things a lot. So on the picture on the left, we have an intramolecular hydrogen bond where you actually have an oxygen and fluorine kind of hydrogen bond happening within the molecule. And you have a situation where they're not hydrogen bonding that way. If you look at the energetics of these two compounds, these are really close to one another in energy. So big problem becomes you have to think about those conformers. Okay, what about the physiochemical properties? Well, there's a lot of importance in knowing physiochemical properties, and two really big ones that we utilize or calculate are octanol and water partition coefficients and lipid water partition coefficients. So a lot of people in pharmaceuticals, they will utilize octanol and water partition coefficients to figure out how hydrophobic or lipophilic a compound is. So they utilize this to figure out, okay, is this compound going to want to be in the blood or is it going to want to be in the fat cells? And then you can actually look at lipid bilayers on, does the molecule want to be in that bilayer or does it want to be outside of that bilayer? So really important for biological systems. And what we can do is we can calculate that. We're trying to build giant libraries where we do this. So what these are, these are called violin plots. You can think about them as box and whisker plots with weighted data. And what we can do is we can functionalize these compounds and we can see how much do these physiochemical properties change and are there any trends we can get from these calculations. Another big one to look at is pKa. So pKa lets you know if the compound wants to be anionic, if it wants to be neutral, or it wants to be cationic. And we can calculate that too. People don't know these properties for these molecules. And what we can show a lot of times is that most of the time, depending on the pH, they want to be an anion. And that's really important when you're going to the mass spec to figure out, hey, how are these things eluting? What solvents do I need? What column should I be picking? Yep. So what you can see here, this is the percentage of anion as you change pH for all of those compounds on this last slide. So basically, if your solvent has a pH of 7 or more, they're always going to be in the anionic form for the ones we looked at. Okay. All right, so what can you get out of this information? So we've made QSSR or QSRR models, and we've predicted new PFAS that they see out in wastewaters. So these are wastewaters from the Philippines, and we determined that these are the most likely probable structures of these compounds. It's the first time that they've been identified. We've also applied this to wastewaters to look at not only PFAS, but a variety of different compounds, such as pharmaceuticals, pesticides, and so on. And what we can show is if you take homologs or compounds that have similar molecular formulas but different structures, we always get the right one when we look at these things. So we can utilize this as a powerful tool to either rule out possible structures, come up with plausible structures, or even confirm the identity of some of these compounds that we see out in the environment. So for the last part of this talk, I just want to thank everybody who's a part of this work. We're funded by the Camille and Henry Dreyfus Foundation and the NSF, but it takes a collaboration from people both at St. Bonaventure and the University of Buffalo to make that happen. Okay, so with that, I'd be happy to answer any questions about PFAS work, about my hydrogen storage, or life in a really cold spot too. Thank you.
Preguntas de esta última parte. Microwave popcorn, anyone? Nadie. So somebody just said they don't want to know about microwave popcorn any longer. You know, and
Yeah.
I have to admit, I found this part absolutely fascinating because I am the resident ethical vegan. So
Wow.
I'm when it comes to hunting, and I'm absolutely terrified of PFAS and the so-called forever chemicals.
Yep.
And I don't know if you saw that recently. There was an article in USA Today about the levels of contamination in the waterways, and yeah, it's pretty scary.
Yeah, it is. Especially because rainwater, at least for the EPA limits, rainwater is not safe to drink by the EPA limits. So I think the EPA limits are a little too low, but it's also concerning that we can detect these compounds in rainwater. So every living creature on the planet is contaminated with these things. There's nothing living that doesn't have them in us. So,
Yeah.
yep, very concerning.
Dudas, preguntas, comentarios, aprovechen. Oh, we have one here.
I'm just curious about your work, like, where do you do these computations? Can you do it on a regular computer or you need like a high performance?
Yeah,
How much time it takes?
Yeah, so that's so for this work, I have a high performance computing cluster to do the quantum chemical simulations. So to put it in perspective, your phone probably has 2 processors in it or 2 cores. Your laptop has anywhere from 4 to 8. I have about 2,000 at my disposal. So so all the quantum stuff, at least for the PFAS compounds, probably takes a couple hours. For the surface stuff, it can take months. When it comes to the construction of the models, though, the statistical models, we do that on a regular laptop, and that can take an afternoon. But it's not like it's really tough. But all the work that we have, where is it? Here for these compounds, there's 151 compounds in this data set. And that took us approximately like 2 months of straight computing time to calculate all of that information. And then to gather it all, that takes even more time. Does that answer your question?
Yes, thank you.
We have a student asking what made you study PChem/computational chemistry.
So when I went to my undergrad, I really liked quantum. I took a course called Modern Physics where I learned everything that you learn in your general physics class is a lie, and I really enjoyed it. And then I was interested in quantum mechanics, but in my undergrad, all my professors were like, it's all smoke and mirrors. It's not really useful. You don't need to worry about it. And then I went to graduate school actually to be an NMR spectroscopist with Dr. Thomas Sipersky. And what we were looking at is we could take an NMR tube, put somebody's blood in it, and we could do some fancy spectroscopy. And what we could do is determine what type of cancer somebody had and what level it was with insanely high confidence. The only one that we couldn't tell apart, I believe, was stage 3 and stage 4 lung cancer. And at that point, it's kind of not good either ways, but it was an awesome diagnostic tool. The problem is you have to sit there and shim very carefully. So you would sit there and you would tweak things, and you had to be doing it every 2 hours. And I just got to the point where I hated that work. I didn't want to do it anymore. And I was going to quit graduate school. And then my advisor, Ava Zurich, I had her for my PChem instructor in graduate school, and she said, "Hey, try this out. I think you'll like it." And I did end up liking it, so I stayed in graduate school. Other than that, I was going to go back and be an environmental health and safety engineer that I was working at. So yeah, that's my journey.
¿Alguien más? ¿En español, inglés? ¿Dudas, preguntas? Anyone? In the other room? We're good?
Okay.
I think everybody got muted with the PFAS business.
Sorry, it's always depressing to talk about it. That's why I hate doing it, but I think it's good. It's good. People are working on things too. People are working on ways to break these things apart. There's a lot of money going towards it. And I honestly think the problem will be solved soonish. And the other thing is we've been living with these in us for quite some time. I think the areas of really high contamination need to be concerned, but everybody else, like I had my well water tested by the U.S. Geological Survey, and there was no PFAS in there. And I live right next to oil wells where they're fracking all the time.
Yeah, yeah, sure. Now, since you mentioned the film, I was wondering, have you read the book?
Yes, Exposure. Yes,
Exposure.
I have. Yep, it's a really good
phenomenal
book.
I read it in one afternoon and I thought, oh, my word.
Yep. I bought it for my mom. She loved it. She said she thought it was very entertaining too. So it's not really like a boring chemistry
No, no,
book.
no. Yeah,
It's an entertaining read. It's pretty funny too, because Bob Billett, who's the lawyer, he is the most personal person I have ever met. I only met him through Zoom, and he was incredibly personable. But you watch him on Dark Waters and you read his book, and you're like, who's this super introverted nerd? But he's a really good guy. He's really outgoing.
so, let's see, anybody else? Nadia, quieren aprovechar? Yes, no? Well, let's thank Dr. Simpson once again for a phenomenal talk.
Thank you guys very much. And if you have any other questions, you can always email me and say hey. Or if you're ever up north and you want to go check out St. Bono's, come on down. I'll say hey.
Thank you so much. I really appreciate your time and your expertise. And we did have some people thinking, and you didn't see some faculty, but yeah, you're really excited their 9 months. That's what I have to say.
Great. Thank you very much.
So
I
much.
hope
You
you
have a
have a great
wonderful
day.
day, Todd.
You too. Thank you.
Thank you so much. We appreciate it. Bye.
Bye.